Hello, today we're going to present our final project, CPD simulation of the centrifugal pump. In this presentation, we will cover these items: introduction, literature review, materials and methods, results and discussion, and conclusions. Now, let me introduce the background of this study. Centrifugal pumps are widely used in many industries such as food, pharmaceutical, cosmetic, and water treatment. They are essential because of their efficiency in transferring energy to fluids. To this, CFD is a powerful tool. It allows us to visualize velocity and pressure files inside the pump, calculate performance metrics such as head, power, and efficiency. In this project, we use STAR CCM Plus to simulate a centrifugal pump designed in Autodesk Inventor, in which two fluids were tested, water and mineral oil. In the literature, several key aspects guided our study. So, first, pump design theory based on classical turbomachinery concepts such as velocity triangles and Euler's equation was applied to define the impeller and volute geometry. Second, previous works like Valdez et al. Provide best practices for CPD validation, including comparison with manufacturer data using error meters. Third, polyhedral meshing with prisms layers was highlighted as the most efficient method for accurate boundary layer resolution. We also found that the viscosity strongly impacts pump performance, reducing efficiency and shifting the best efficiency point. Finally, direct cavitation analysis using total pressure, their shielding was identified as a powerful technique to detect cavitation zones with precision. Well, so for the development of this CFD study, we used several key resources. First, Autodesk Inventor was employed to design the pump geometry, including the impeller and volute following the required dimensions. Second, the CFD simulations were carried out in STAR CCM Plus, where the machine, physical setup, and numerical analysis were performed. We also use a workstation with a multi-core processor and parallel computing, which allowed us to handle meshes with more than 1 million cells. As working fluids, we select water and mineral oil at 20 degrees Celsius since they provide a good contrast in density and viscosity. And finally, manufacturer operation curves were used as reference data to validate and compare the results of our simulations. In this study, the pump geometry, including the impeller, volute, and rotation region, was designed from scratch in Autodesk Inventor and then imported into STAR CCM Plus for meshing and simulation. We test three mesh configuration cores, fine, and a reference mesh of about 1 million cells using polyhedral elements with a prism layers to ensure a good balance between accuracy and computational cost. The reference mesh was selected after a mesh independence study at the best efficiency point. In total, 10 simulations were performed, 5 with water and 5 with mineral oil, at different flow rates, including shut-off, intermediate, best efficiency point, and free delivery. Finally, post-processing, including validation of performance curves against manufacturer data, visualization of velocity and pressure files, cavitation analysis, wall plus distribution on the impeller, and flow animations to illustrate pump behavior under real operations conditions.
The curve for water exhibits the characteristic shape of a centrifugal pump, with a maximum head of 138 meters at cutoff, gradually decreasing to 109 meters at a maximum flow rate of 210 cubic meters per hour. For the mineral oil, the curve is consistently lower, showing an average reduction of 40% in general head across the operating range. This significant performance drop is directly attributed to the higher frictional losses associated with the oil's high viscosity, which dissipates a substantial portion of the energy impaired by the impeller. The maximum efficiency with water reached 65% at 170 cubic meter per hour (BEP). For the oil, the maximum efficiency did not exceed 60%, and the BEP shifted to a lower flow rate. This shift and reduction are typical phenomena when pumping viscous fluids, as frictional losses alter the system's optimal operating point. To validate the accuracy of the CFD model, the results obtained for water were quantitatively compared to the manufacturer's experimental data using the mean square error and root mean square error. The RNC value represents a deviation of 6.35% from the maximum head and 8.04% from the minimum head. This error below 16% falls within acceptable limits for centrifugal pump CFD simulations and validates the model reliability in predicting hydraulic performance. The error band of a plus or minus 30.4% for efficiency indicates acceptable accuracy in predicting this parameter, which is inherently more complex to calculate due to its dependence on torque and mechanical losses.
Cavitation was analyzed by post-processing the CFD results to show areas where the absolute stake pressure was lower than the vapor pressure on the plate. For water, vapor pressure is 2340. The results show a small and solid spot on the suction side of the impeller blades, where the pressure dropped below 2340. This is clear visual evidence of early cavitation. Under these operating conditions, since the low pressure zones were small and localized, the cavitation is only beginning. For mineral oil, vapor pressure is like zero. The results showing some pressure value significantly below zero. It's really is really negative absolute pressure is not possible. These values are likely numerical errors in the simulation caused by things such as poor query cells in region with strong flow gradients, convergence error in the pressure calculation, and solver pressure limits when pressure values are very close to zero.
Velocity counters reveal further evidence of the viscosity effect. For water, velocity streamlines are well distributed across the impeller and pollute, reaching maximum values at the outlet as expected for efficient conversion of energy. For oil, the velocity field is less uniform, with reduced outlet velocities and higher recirculation zones, particularly at the intermediate flow rates 150 170. These patterns demonstrate that viscose effects suppress float acceleration and increase hydraulic losses. At maximum flow rate, water maintains continuous acceleration, while oil shows deceptive velocity patterns, reinforcing the 40% head loss previously quantified. With both fluids, the pressure fields show the same radial gradient from the impeller eye, low pressure, towards the volute outlet, high pressure. However, there was substantial difference between water and mineral oil. At the shut-off, both fluids displayed maximum pressure built up near the impeller. Still, oil had a more concentrated pressure area, which aligns with increased energy losses. In the higher flow rates, water had a much smoother, more homogeneous pressure field, whereas oil experienced increased low pressure areas, indicate of the dissipated effects due to water's viscosity. In the best efficiency point, water exhibit a more efficient energy transfer, whereas oil's pressure field continued to remain subdued, indicating a decrease in generated heat.
The wall Y plus is a key parameter in CFD that tells us how well our simulation captures the flow or flew right next to the pump walls. In all our simulation, the Y plus values were consistently below 5 for both water and oil across all flow rates. This is ideal. It means our model accurately resolved the thin boundary layer, which is important for reliably predicting friction losses and pump efficiency. We also saw the expected trends. Y plus increased with flow rate due to higher shear stress, and it was lower for the more viscous oil, which confirmed our CFD setup correctly responded to the physics of different fluids.
In this project, we applied CFD to study the performance of a centrifugal pump using water and mineral oil as working fluids. With water, the pump followed the expected performance curves, reaching its best efficiency point close to uh, 170 cubic meters per hour. In contrast, with oil they had dropped by almost 40% and the best efficiency point shifted to a lower flow rate, showing how viscosity strongly affects pump behavior. We also analyzed cavitation for water, small low-pressure zones on the section side of the impeller indicate the beginning of cavitation, while for oil, the results show no cycle negative pressures, which were numerical effects. Overall, CFD proved to be powerful tool to validate points performance, understand internal hydraulic behaviors, and anticipate problems such cavitation without relying only on physical testing.